Okay, so project, go ahead, Austin. You want to shut the door for me, CJ? Thank you. Project 5, you can either hand in on Friday or Monday. If this is the carrot, if you want to hand it in on Wednesday and it's completely done, I'll grade it, hand it back to you on Friday so you have another chance to get like 32 out of 32. Then you can rehand it in on Monday. Okay, so that's project 5. The median grade for exam 3 for both classes was 80.5. And today's material is supplemental. It's not in your textbook. You won't have a homework on my math lab. I've created some homework problems for you. But I first want to finish up, let's finish up the couple of problems from lecture 36. Starting with this one. So lecture 36, I think on yours it was number 4 or 5. What number is it? 5. Mine is a little off, so. All right, so when this was right after we had learned how to solve exponential functions. And when you look at these, it doesn't look like anything that you saw previously. And that's because you have to look for a common factor. So if we notice in this first equation here, the first equation is set equal to 0. That's always a hint about your strategy, because you know that when you have an equation set equal to 0, if you can represent it as a multiplication problem on the left side, then you know how to solve it. So is there a common factor, and what would it be in the left-hand side of this first equation? What would the greatest common factor be? The left-hand side. What do you see? You see an e to the x. Do you see anything else that they both have? And an x, right? X times e to the x, okay? So you're going to factor out, that's your first step. You factor out x times e to the x. And let's see what you have left. You're going to have two things inside since you started with two terms. So x times e to the x times another x will give you this first term up here. That's your x squared times e to the x when you multiply it. And then what do we need to put in here for our second term? 5, right? So we're all set. Now you set each factor equal to 0. Here's factor number 1. Here's factor number 2. And this binomial is factor number 3. So we set each factor equal to 0 and solve for x. Well, there's nothing to do with the first factor. X equals 0 is done. That's just first solution. Done. Now your next one says, what value of x is going to make e to the x equal to 0? Well, let's take a look at the graph of the function y equals e to the x. So here's our exponential function, e to the x. It goes through 0, 1, and when x is 1, our value is e. So when is that going to equal 0? When will the output of this function be 0? Never. It never hits. Because remember, your horizontal axis here, your x-axis is the horizontal asymptote. So never ever can this be 0, because we know our range for an exponential function is 0 to infinity, not including 0. Will never be 0. There's no value of x you can put in there that will give you 0. Okay, and then finally we got a little baby linear equation here, and this is going to be 0 when x is 5. So your solution set for this particular equation, if you were writing this in my math lab, you know how they like you to write the solution set, would be 0, 5 with the little braces. All right. Now, the next one looks really complicated, but we start off the same way we always do when we're trying to solve something that's not linear right away. We hope that maybe there's some trick we could learn with setting it equal to 0. So let's subtract 2 times 10 to the x from each side. So we're going to subtract that from each side. Okay. Now let's do a little something here. Let's cover up the 10 to the x for a minute. Okay, once you get that, let's cover up the 10 to the x. Can I cover it up? I wanted to do something cute, and I'm not going to be able to do something cute. Can't do cute? No, I guess I can't do cute. Let's see. How do I get that down there? Over here? Come on. Oh, there we go. I want to cover that up. All right, so we're going to cover up the 10 to the x. Here we go. Copy, paste. So it's not there. I believe it's not there. You just see a big heart. Right, there we go. That looks better. Do you see a common factor all the way across there? I don't. All right, the heart's covering it. But now this equation is x squared. I love x squared. Take away I love x. Take away I love 2. So love is part of the equation. Do you see a common factor? Do you see anything common to every single term? Love. Love is common. We love these equations. So pull the love out front. Pull the love out front. And what do you have left when you pull the love out front? What's left? Up. Okay. And how do we, what kind of, this is a second degree trinomial. X squared minus x minus 2 trinomial means 3 terms. It's second degree. So how do we factor that? How do we factor that? X minus 2, x plus 1 equals 0. So to solve this equation, we set each factor equal to 0. So we set love equal to 0. Well, that's when you're in really tough straits, right? When love is equal to 0. No loving going on. We set x minus 2 equal to 0. And we set x plus 1 equal to 0. And we solve each one. In this particular case, x is 2. In this particular case, x is negative 1. Let's reveal the heart. We pull the heart off. What goes in place of the heart? 10 to the x. We take the heart away because that was messing with our brain, seeing all that 10 to the x. So when is 10 to the x equal to 0? Ten to the x, when does that equal 0? Never, because that if we were to graph it, it would look like this. Just like the e to the x, except for this one goes through 0, 1, and 1, 10. So that an exponential never equals 0, so that's a never. So here's our solution right there, 2 and negative 1. You're done. Okay. So you had these two equations last Wednesday, and we didn't get to it. I don't know if you had any homework like that, or if you have any homework like that, but I wanted to cover those for you. Huh? What did you say? Yeah, well, that's because I haven't put them all up yet. Really? Yeah, really. Oh, well, I didn't tell you to go get all excited now about anything. Okay, so if you came in late, a couple of you did, today's information is supplemental, which means it's not in your textbook and there's no My Math Lab homework attached. I wrote up a separate homework at the end of this. And what I said to the other class is everyone should do the homework because it's not just on today's material. It kind of combines some stuff. It would really give you a nice summary of these ideas that we're going to talk about today and some of the ideas we've talked about previously with exponential functions. If you want to hand it in, I'll grade it for you, but I'm not going to input it formally into your homework section. So this is where you get to be your own determiners of whether you want to do the homework or not. I recommend it, of course. So yesterday I was saying, what is this class missing? I looked at the schedule and I saw that I had given 2 days for exponential and log functions, and except for that one problem, we covered it in 1 day. I didn't want to go to lecture 39 yet. So I was like, yeah, there's something else we can do to try to bring this idea of exponential functions and the difference between exponential growth and linear growth together. And also, regardless of whether you're in the BAT program and you're transferring, or you're an environmental science person, or a straight science person, or a health science person, you will see exponential growth factors reported as rates, as percentages in anything you read. And so the question is, they report it as percentages, but how do we go back to our exponential equation? And we haven't done anything quite like that. So yesterday was a glorious day. I graded the exams, I did all your grades for you, and then I decided to write up a whole new lecture note and homework set. So needless to say, I didn't have any time on Sunday until about 8 o'clock. And then I was too tired to do anything, except for play with my new kitty. All right, so here's, I think, some data that you are all pretty familiar with, right? The Rabbit Utopia data. And so the question that we're going to be asking for the next 15 or 20 minutes is, if we're looking at a data table, how do you determine whether the data is linear or exponential? So what I'd like you to do at your seats with your table mates is to identify which of these functions first is linear and which one is exponential. And then how would you describe how the population changes from one year to the next when you have a linear function and when you have an exponential? And then when you're done, I'll ask you each for this description from your tables. So talk about it after you do it, come up with a sentence, and then I'll ask each table to report back in. Use your flags when everybody's done and you've talked about it. Oh, guess what? I haven't been recording. Have I? Oh, I have. Okay, so first of all, which one of these functions, P or R, is linear? P is linear. You're hoping you're getting a question like this, right, on your final, right? Yes, okay. And therefore, R is exponential. All right. Again, we've worked on this, so hopefully that part wasn't too bad. Okay, so we've identified which function is linear and which one is exponential. We've done that. Now, how would you describe how the population, the number of rabbits, changes from one year to the next using this linear function? How would you describe it? Cooper? Oh, Jonah, you have your hand? Okay, I'll go with Jonah first, sorry. Okay, the population of rabbits increases by 1,000, what'd you say? Every single year. Now, in my first class, we wrote down 4 different sentences, all added something, no pun intended, something to the overall discussion. So I'm sure not everybody wrote exactly that sentence. So someone else want to tell me what they wrote? CJ does? The rabbit, excuse me, CJ, the rabbit population increased by 8,000 each year. Okay, someone else? Someone else have another way that they said it? What did you have, Ben? Excuse me? It adds okay, I just want to write first what you said. It adds by the same amount each year. Okay, so it being the population of rabbits adds by the same amount, being 1,000 each year. Okay, Gina? Okay, so that's the other thing I was looking for. The rabbit population, because it's the same idea, but stated a little differently. So say it again, Gina. The rabbit population increase. Ooh, I even like that. At a steady rate of 1,000 rabbits. What, each year? per year. Okay. So they all are saying the same thing. They all are expressed a little differently. What Gina just expressed, steady rate. Steady we often refer to with the word fixed or constant. Rate of change between 2 units, rabbits, and time, we commonly refer to as the slope, right? So Gina worked in the idea of the constant rate, which means that we add the same, what Ben says, we add the same number from one year to the next. Okay, that's what all of you said in a different way. So if you were looking at a data set, okay, you first of all look at the difference in your years from 0 to 1, right? You look at the difference. Each of these is consecutive. So the change in your years, the change in t is 1. 1, 1, 1, 1, 1. That's the difference in your independent variable time. And then you look to see if the change in your rabbit population is also the same from one year to the next. And you can see that it is constant. So some books refer to that 1,000 as the first difference is constant. Okay, the first difference is being the ratio of 1,000 to 1. That's the slope. Okay, so you see that as we calculate the differences from year to year in the rabbit population, it's constant. Boom, automatically linear function. All right, so that's how you tell a linear function. Now, let's do a similar thing, but with the exponential function. So then you move down and you say, okay, I have a unit increase. I have an increase of 1 in my years. And let's see if I have a constant increase with my rabbit population. Well, I go up by 1,000 here, and then, oops, the minute you do that, you know automatically it's not linear because it's not a constant rate of change. You're not adding the same amount from year to year, however you described it. So let's just continue with this, looking at consecutive values of my output, my rabbit population. So here are consecutive values of my output, the change in my R of t from year to year. And if I look at that, I see that it's not constant. But what is constant? What is constant about that? It's doubling every year, right? So if you look, and how do you get double? You say, well, if you go from here to here, you go by 2, by 2, by 2, by 2. It's doubling every year. So how would you describe the exponential change, Gina, from year to year? What did you write? The population of rabbits is doubling from year to year. Anybody got anything different than that? Population of rabbits is doubling from year to year. Okay, so if you're looking for this doubling, this is a constant factor. That's the difference. Up here you had a constant rate, 1,000 rabbits per year. Now it's a factor. It's a number you're multiplying by from one year to the next. So you're multiplying by a constant factor. How do you find that factor? Well, you take the growth in rabbits from year to year, and you look at the ratio. And as long as that ratio is the same, then you know you have an exponential function. So if we compare 2,000 to 1,000 as a ratio, as a division problem, you get 2. 4,000 divided by 2,000 is 2. 8,000 divided by 4,000 is 2. So notice that number, that constant ratio, 2, becomes your growth factor in your equation. This constant ratio is your growth factor. That's your base. Remember, that's the base of your exponential equation, right? That's the base, too, because it was doubling. So let's take a look at the equations now for each of these functions. So here's our linear equation, and I'm going to introduce some new language for you about linear and exponential. The growth of a linear function is what we call additive. Additive. And what this means is each year that passes, we add 1,000 to the number of rabbits. So it's an additive. Now, if we had a negative slope, we would be subtracting that constant, but we still call it additive because remember, subtraction can be rewritten, right, as addition of the opposite. So when you add or subtract an amount each year or each time period or whatever the independent variable happens to be, it's called additive. Notice the 1,000 here is your initial, this is your starting population, your starting value. And where do we find that starting value if we were to graph this? Where would we find that starting value of 1,000? Where would that be located on the graph? The y-intercept, right? Y-intercept. Okay. This is your additive. This is the amount you're going to repeatedly add. We're going to repeatedly add 1,000 depending on how many years we're looking at. So this is the repeated sum. 1,000 plus 1,000 plus 1,000 plus 1,000, depending on how many years we go out. The growth of an exponential function is multiplicative. There's a difference. Multiplicative means that for each year that passes, we multiply the number of rabbits, in this case by 2. So this is still the starting value, your starting population of 1,000 rabbits. Now notice we're multiplying, we're repeatedly multiplying by 2 depending on how many years we go out. So this is our growth factor. Our growth factor is the base of our exponential function. Okay. So generally speaking, we can describe any linear function or any exponential function. We have an output. The output will always be our initial quantity, whatever that initial quantity is. If you want to think about this case, it's 1,000 rabbits. With a linear function, it's the rate of growth. It's the rate of growth in the rabbit population. Sometimes that rate, if we have a negative slope, would be a rate of decline, times your input, the number of years. An exponential function can always be written as an output is your initial quantity times your growth or decay factor. Now your independent variable is your exponent. Okay. So remember, if your growth factor is, if your factor is a growth factor, then it has to be greater than 1 if it's a growth factor. And what must be true if it's a decay factor? What must be the value for the base? So it can be negative. So it's a fraction or a decimal between 0 and 1, right? So when we have a decay, if something's decaying, we would expect to see a fraction as the base or a decimal as the base. When it's growing, it's a number bigger than 1. All right, so in conclusion, we can say that linear functions represent quantities to which a constant amount is added or subtracted for each unit increase. Unit just means an increase of 1 in the input. And exponential functions represent quantities that are multiplied by a constant factor for each unit increase. So that's the difference between when you're looking at a table of values and you're trying to determine which one is linear and which one is exponential. So the only thing I want you to change on this next thing is, let's see, determine whether the function is linear, and then did I say anything else? Nope. Okay, so there's your opportunity now to determine which of these is linear and which of these is, I don't want you to write the equation though. Cross that out. I just want you to determine which is linear and which is exponential. And say how you know. Okay? And when you do that, just put up your flags when everyone at your table's spinning. So which one of these functions is linear and which one is exponential? Cooper? So f is linear, the function f is linear, and that leaves the function g as exponential. Okay. So let's take a look at how you determined that. So what did you do to determine which one was linear and which one was exponential? What process did you go through? Austin, what you do? Okay, so given that this is constant, the change in our x is so we call that the difference up between our x. That little delta means the change in or the differences, right? Between our x values is 10, between consecutive x values, right? So we've got that set. So really we only have to pay attention now to the changes in our output because the change in our inputs is constant. So the change in our output, our successive outputs for f is 30, so that's constant. So we know that that 30 to 10 is constant. It is the same as 3 to 1 or 3, so that's a linear function. So the difference between our successive values in f for f, the function f, is constant. Okay, f of 35 take away, excuse me, f of 10 take away f of 0 is 35 minus 30, which is, I'm going too fast. 35 minus 5, which is 30. And then if we went to the next one, f of 20 take away f of 10. These are successive outputs. F of 20 is 65 minus 35, that's 30. Okay, so that's just how we would write out what we just did here with these little carets with the 30. Okay, then what about the exponential? What did you notice with the exponential function? Someone else want to tell me what you noticed? Well, first of all, why isn't it linear? Amy? Were you starting to talk? Someone was starting to talk. Okay. Well, what told you to do the ratio first? What did you notice first? That goes up by half. So you're saying half of 20 is 30, half of 30 is... It adds on, so it's 20 plus 10. Yep. But did you check to see if the difference between consecutive values was constant? I noticed that wasn't. Oh, so that's really the first thing you noticed, right? So if you check the difference between successive values for g of x, so here are two successive values for g of x, the difference between those values is 10. Then if you do it again, the difference is 15. So the first thing you notice is that if you calculate successive values for g of x, it's not constant. So you definitely know it's not linear. So then you have to check to see if it's exponential. It may not be either one of them. There may be some other function that's going on. So next you check to see if successive ratios is constant. So let's see. The first ratio is 30 to 20. Is that the same as 45 to 30? They're both equal to 3 to 2, which is 1.5. So yes, if I did this all the way out. And what Amy noticed is really interesting. She says, if I take half of 20, and I add it to 20, I get my next value. It's 20 plus 30, 20 plus 10 is 30. And if you do that all the way up, now go 30 to 40. If you start with 30 and you add half of 30, you get 30 plus 15, which is 45. If you now start with 45 and you add half of 45, you get 45 plus 22.5, you get 67.5. So she noticed an interesting thing. We'll get to in a minute. So we call 1.5 a growth factor. Notice it's bigger than 1, right? So you're growing. This is our growth factor. But that represents the growth factor. The ratios are constant at 1.5 when our change in x is 10. So this 1.5 represents the 10-year growth factor. It's not a yearly growth factor. It's over 10 years. It's a decade growth factor. Okay. So it's really interesting how Amy thought about this, because I want you to take a look at this for a minute. Let's take a look at this first equation. 20 plus 0.5 of 20. And I'm going to just write something in front of this 20. I'm just going to call 20 1 times 20. Can you see the 1.5 in there? If you pull out a common factor of 20, you have 1 plus 0.5 left, which is 20 times 1.5. So when you write it this way, 1.5, that's your constant ratio. Or, I keep saying this, your growth factor. When you take 1.5 and you divide it up into the amount you started with, the 1 plus the half, notice that represents 50%. So we say the growth rate, not the growth factor, it's different. The growth rate is 50%. And that's how it would be reported if you were reading something. If something was growing at the rate of 50%, its growth factor is 1.5. Because you take 50%, you make it into a decimal, and you add it to 1. So that's how you go from a rate to a growth factor. So let's take a look at that in a little more detail. So before we actually get there, I've got just one other little thing for you to do. So I might do something like this. Give an example of an equation that models the growth of a population. So this would be a nice final exam question. Give an example of an equation that models the growth of a population that starts with 200 cells and triples for every time period called T. How would you write that equation? What would it look like? I'll be the writer. You want to start it, Cooper? Not do the whole thing? No, I don't agree. F of x. Someone else want to help? F of t, there we go. Our independent, you're not an amateur. Our independent variable is t. So when we write our function, t must be our input, right? We're so used to saying x that sometimes we don't even like really fully read the equation. So Cooper's turned off. I put an equal sign. Someone else want to give us the next little part of this? The next little part. Not the whole thing. 200, going once, going twice. So Ben's turned off. Was it Ben that said 200? Yep, okay. And now the last part of this. Times 3 to the t, right. So what was the dead giveaway that made you know that the example, the function you were going to write was an exponential function? What was the dead giveaway? Triples, right. That's multiplicative, right? That's a constant factor times 3. Okay. I'm not that interested in the next one. I thought I was when I wrote it yesterday, but we'll leave it. Let's carry on here. All right. So, someone want to read number 4 for me, Connor, in your wonderful DJ voice?
Population growth rate
Stop right there. This is the whole reason why I wrote and spent hours of my life yesterday, is just for this thing right here. Beside the tables, I wanted you to be able to look at tables and know when something was linear versus exponential. So say that again, Connor.
Population growth rates are
Okay, keep going.
How do we convert these percentages of growth rates into factors?
Okay, so Gina helped us already. Not Gina, Amy helped us already when she said, I noticed that to go from 20 to 30, I take half of 20. And when I go from 30 to 45, I take half of 30 and add it to 30 to get my 45. She already helped us with this idea. Thank you, Amy. So, as you noticed, I've been talking about tuition rates at colleges, and particularly private four-year colleges. And part of this is my concern about being able to get my oldest daughter through college. So, this is almost totally true. I couldn't find the bill because I left it on my desk, but this is roughly the figures when I was writing this yesterday. Private tuition at four-year colleges, it's reported. When you look at this on the internet or in a news article, they're not going to give you the growth factor, they're going to give you the growth rate. So this first sentence, tuition at private four-year colleges is growing at the rate of 6% per year. Okay, this is called the growth rate. Another way to think about exponential functions is that they're being multiplied in successive outputs is being multiplied by a constant percentage. You can think of factor, you can think of number, but if it's being multiplied by a constant percentage, that's another way you know that you have exponential growth. So the minute you read a sentence like that, you say exponential growth, exponential growth. If the current tuition at Warren Wilson College in North Carolina is $38,400, the 38 part is right. I couldn't remember how many hundreds of dollars it was, so I just made up something that was easy. 38,400. Then write a function to model the growth in tuition over time. So I'm going to be interested in being able to calculate so I can plan what my daughter's tuition will be for the next 3 years, because I'm hoping she goes in as a sophomore, since she earned 30 credits at GCC before going to Warren Wilson. So here's the current tuition. This is like at time 0. So if I were doing a table and T was time and this was my cost, at time T equals 0, it's 38,400. So now I want to calculate what it will be next year, and I'm going to use Amy's idea. Amy's idea said I take my initial value and I add something to that, a constant percentage. It's 6% of 38,400. So I can figure what that is by using my calculator, but what I want to do first is I want to show you the idea of how to see this constant rate as a growth factor. We could actually calculate that if we want, but that's not what I want to do right now. Notice if I factor out 38,400, what would I have inside the parentheses if I pull 38,400 out? What would be my first term? What number? 1 plus 0.06, right? 1 plus 0.06. So that would be written as 38,000 times 400 times 1.06. This will give me the tuition next year, and it's pretty darn close because this is close to the bill I saw when I got her financial aid information. So let's get this calculator out if I can. Okay, so let's see what it will be next year. 38,400 times 1.06. I know it's 40,000 something. I don't remember so it's going to be 40,704. Okay. So if I want to write an exponential function so that I can look at the next year and the next year, and God help us, I hope she doesn't have to go 4 years. What would the exponential function look like that would calculate that I could then look at successive years? I know the rate. The growth rate is 6%. R equals 0.06. To get the growth factor, what did I do? I added R to 1, and there it is. So what would the overall function look like? Well, we called it C of T up here, so let's keep it with C of T. The cost over time. What's my initial amount? What do I put for A sub 0? 38,400. And I have 1.06 as my growth factor raised to the T. So let's see. But what she's going to cost me in a couple of years here. Oh, it's not much difference. I don't know. We'll see. Oh, really? Well, she doesn't cost me that much money. Yeah, 1.06 raised to the x. Okay, so we're going to start our table. Let's say we'll let x be 0. It will be the first year she's there. And then we're going to increment by a year. So let's go to our table and see. Okay, that's not the table I want. I don't want the graph. What did I do? I know what it's going to look like. Come on. I hit the wrong. I got to wait for this to stop thinking. So let's go to the table and let's set this up automatically here so I can really freak out. Second table. So here I am. If she were going this year, it'd be 38. Next year, it's going to be 40,704. Now look at the difference. This was less than $1,200, right? From now until next year. But then look what happens. Because it's growing exponentially, it starts increasing pretty quickly. So her second year would be 43, and her third year is 45. If she has to go 4 years, it's up to 48. So exponential growth increases very rapidly. Okay, compare that to an exponential growth of adding an amount every year. You can see that exponentials are much more powerful. Let's take that out. Take a little picture of that. Oh, here we go. Let's not do that. Ever since they've done this. Okay, now let's take a picture. I'll just put this down here for you so you can see it later. All right. So if you have any kids that are college age, you should start sweating now. Or if you're paying for your own college, start sweating now. Or go to public colleges. There you go. Much better. All right. So we've talked about exponential growth. How do we convert these rates if it's a decay? If something's decaying versus growing. So yesterday I was reading, I got this right off the web, and here's the URL. There was a NASA report about perennial sea ice for the Arctic, actually. And perennial sea ice is the sea ice that doesn't melt over the summer and it stays all year long. So they've been actually recording the area of perennial sea ice over. So if I had done this a couple of years ago, this rate would have been a lot less. The rate has actually increased pretty rapidly. So it says, according to recent studies done by NASA, perennial sea ice is melting at the rate. So the melting tells you it's going to be a decay. It's melting at the rate of 12.2% per decade. So our input here is going to be the number of decades. If this rate stays constant, find an exponential decay function that represents this decline. So the first thing you do is you find your percentage. Your percentage is 12.2%. Then you convert that to its decimal equivalent, which is 0.122. But now you're not adding it to 1, you're going to subtract it from 1, because remember, now your base has to be a number between 0 and 1 because it's a decay, an exponential decay. So your decay factor is going to be 1 minus r, which is 1 minus 0.122, which is 0.878. So now when you write your exponential function, you have your initial amount, you have your base. Your base is going to be a number between 0 and 1. In this case, it's 0.878. And you raise it to D. D here is the number of decades. Okay? So if we wanted to try to figure out how long it was going to take for this particular amount to, say, be half of what it is now, then you could do the following. You could now answer these types of equations, these types of questions, even though you don't know what the initial amount of a subknot is. How long before we have half the amount of perennial sea ice? Well, what would be the value of f of d if we were going to have half the amount that we have right now? How would I write it? Half of what we currently have. How much do we currently have? How much perennial sea ice do we have right now? Right now means time t equals 0. How much do I have right now when t equals 0? Oh, excuse me, d. D equals 0. No. What's the value when d equals 0? Okay. F of 0. What's 0.878 to the 0 power? 1. So f of 0 is a sub naught times 1. This is our initial amount. That's what the little sub naught means. It's always the amount you start with. That's your starting value. So your starting value, f of d, is going to be a sub naught. So how do I represent half of that? I'm trying to find out how many more decades I'll have half the amount of perennial sea ice I now have. How would I represent half of that? Divided by 2, right. So f of d, which is the output I'm trying to find, I want to know when it's going to be half of what I currently have. I put half of a sub naught equals a sub naught times 0.878 to the d. And I want to solve this for d. So this goes back to what we did last week. To solve this for d, I want to get a 1 out in front. So I divide both sides by a sub naught. And on this side, I get 0.878 to the d. And what do I get on the left-hand side? Half of a sub naught divided by a sub naught. What do I get? One and a half? Point 0.5 times a sub naught divided by a sub naught, folks. 0.5. This cancels. If I asked you for something to double, it's just 2 times the initial amount. Half of what's there is half the initial amount. So you get 0.5 over here. Now, how do you solve this exponential equation? What are you going to do to solve that? How do you undo an exponential? What's the inverse of an exponential? What's the inverse of all exponential functions? You don't know the inverse of an exponential function? What kind of functions are these? I have failed you. What's the inverse function? What? It's logs. Logs are inverses of exponentials. They undo each other. So you take the log of both sides. It doesn't matter which log you take. The d comes down in front. To solve for d, you divide both sides by the natural log of 0.878. So let's see how many decades before we have half the ice we currently have at a melting rate. That's if it stays the same. Let's see. Let's see how long it's going to take us. Natural log of 0.5 divided by, when things are growing or decaying at an exponential rate, that's when you got to start getting really, really nervous. Let's see. Oh, what did I do? An extra parenthesis? Oh, thanks. Okay, so that says roughly a little more than 5 decades. 5 decades is 50 years from now. I won't be alive, but I'm still going to worry about it. Okay. I didn't plan that question. It was a pretty good question, though. When I wrote that yesterday, it just came to my mind as I was doing this with you. I'll have to add that. Okay, so let's quickly do 1 or 2 of these, folks, and then I want you to get to your group activity. So let's find the growth or decay factor if I give you a rate. So suppose the bottled water industry in the US is projected to grow at an annual rate of 12.7%. How do I get my growth factor? How do I get my growth factor? So this is my growth rate. What are we calling growth rate? What little letter are we using for that? R. R equals 0.127. You change it to a decimal. Now to get the growth factor, how do we get the growth factor? Plus 1, right. Growth factor is 1 plus R, which is 1 plus 0.127. So 1.127 would be the base of your exponential. There it is. There's your growth factor. So if you were putting this into an exponential equation, it would look something like this. Some initial amount times 1.127 raised to the t. There's your base. That's your growth factor. If you wanted to go from your growth factor backwards, if you wanted to go back to your rate, all you do is subtract 1 from this and you get 0.127, which is 12.7%. The population of Nigeria is currently is 2.7% a year. That doesn't sound like a lot, but the US is under 1%. So how would we write the growth factor? What would the growth factor be? Someone want to help me with this one? What would the growth factor be? Cooper? 1.027. So let's see. Let's go backwards. 1.027, take away 1 is going to give me my R. That's 0.027. And 0.027 is the same as 2.7%, right? So basically R is 0.127. To get my growth factor, I add those two together and I get my growth factor. And similarly, if we do it the other way, I was debating between caffeine in the body and blood alcohol content, and I went with caffeine. Since I know not all of you are 21 or older, couldn't even talk about that. So the amount of caffeine in the body decreases, so automatically, what type of number are you going to have for your factor? Is it going to be a number bigger than 1 or a number between 0 and 1? 0 and 1, because we're talking about exponential decay. So for C, R equals 12.129. That's 12.9%. And to get our growth factor, we subtract it from 1. 1 minus 0.129 gives us what? 1, help me, 7, 8.871. Yep, so that would be our growth factor. So if we were writing an exponential equation, it would look like this. Okay, so anytime you notice your base is a decimal instead of a number bigger than 1, you know you've got exponential decay going on. So I wrote a huge group activity. You're not going to be able to get through the group activity. You'll probably only be able to get through this table before you leave. If you want to do the drug filtering, this is about drugs in our body and our kidney metabolizing drugs. This is a really good problem. And then here's your homework. And again, I mentioned I will gladly grade your homework, but I'm not going to put it into my math lab because I don't know how to. I guess I could figure it out. But basically, you have between now and next week, if you want to hand it in by Monday, I'll get it to you, back to you. Okay. So no my math lab homework. I wrote up these problems for you to do. So hopefully before you leave, I'll be able to grade your table. If you've got that done, work on the drug filtering.